Dear students, you know that I am taking class on rings and fields, and in the last class I have started subrings. Okay, so now today I will take some theorems on subrings. So first theorem says that a subset S of a ring R is a subring of R if and only if first one, for all A belongs to S, B belongs to S, A minus B implies A minus B also belongs to S. Similarly, second one, for all A belongs to S, comma B belongs to S implies A into B also belongs to S. Okay, so this is the theorem we have to prove. So proof. So we know that here if and only if is there. So we prove the theorem by necessary and sufficient condition. Okay, so first what we assume, let the subset S of a ring is a subring of R. Okay, so let a subset S of a ring R be a subring. Okay, so when it is a subring, then by definition of a subring, it is a ring by itself, right? So this implies S is a ring by itself. That means it satisfies the properties of rings. That means it satisfies law of addition, it satisfies law of multiplication. Okay, so like that. So now say therefore A belongs to S implies minus A also belongs to S. So minus A belongs to S and B belongs to S implies, add these two, so that is A belongs to S, then B also belongs to S, which implies when B belongs to S, minus B belongs to S. Okay, so now from these two conditions, so A belongs to S comma minus B belongs to S implies, means A belongs to S and minus B belongs to S means law of addition holds because S is a ring. So A plus of minus B belongs to S, or in other words A plus into minus, it becomes minus, A minus B belongs to S. A minus B belongs to S. Now similarly take the second one. For all A belongs to S, for all B belongs to S, which means that for all A belongs to S and for all B belongs to S, which implies AB belongs to S because S is a ring, so law of multiplication holds. Law of multiplication holds true. Okay, so therefore this is the necessary condition. So this is the necessary condition is proved. Next, conversely, we take conversely. Let for all A belongs to S, B belongs to S, A minus B belongs to S. Okay, then similarly second one is what? For all A belongs to S, B belongs to S, A into B belongs to S. So now we prove S is a subring. Now we prove S is a subring, right? So now take this one. So now for all A belongs to S, comma B belongs to S, okay, A minus B belongs to S. Okay, this implies A plus of minus B belongs to S. So this means law of addition is proved. Okay. Now similarly, take the second one. For all A belongs to S, comma B belongs to S, AB also belongs to S. So this means law of multiplication is also proved. Okay. So which means, so when this law of addition holds true, when the law of multiplication holds true, so when then when these two laws holds true, then automatically the other two laws, that is the distributive law, also holds. The distributive law and associative law also holds, because it is no need to prove this one, because already it is understood. When this law of addition means the associative law, it involves addition of two numbers, so associative law also holds. Similarly, distributive law means here the law of multiplication holds, A dot B holds, so distributive law, there is the term A dot B, so therefore distributive law also holds and associative law also holds. So therefore S is a subring. So this is the proof. Okay, next we prove another theorem. Theorem 2. So it states that the intersection of two subrings, is again a subring. Okay, so this we have to prove. So proof. Here we take two subrings, say S1 and S2. So here let S1 and S2 be two subrings. Then what we prove? We prove S1 intersection S2 is also a subring, right? So now let A belongs to S1, comma B belongs to S1. A belongs to S1, comma B belongs to S1, and similarly, okay, B belongs to S1. Then let AB belongs to S1 intersection S2. Let AB belongs to S1 intersection S2. So which implies A belongs to S1, comma B belongs to S1. A also belongs to S2 and B also belongs to S2. Right? So when A belongs to S1 and B belongs to S1, right? So it implies, by using the previous theorem, A minus B belongs to S1. And similarly here A belongs to S2 and B belongs to S2. So by previous theorem, A minus B also belongs to S2. So when A minus B belongs to S1 and when A minus B belongs to S2, means A minus B belongs to both S1 and S2, which implies A minus B belongs to S1 intersection S2. Right? So similarly here A belongs to S1, B belongs to S1, it implies A dot B also belongs to S1. Similarly A belongs to S2, B belongs to S2, it implies AB belongs to S2. This is by previous theorem. Okay, so when AB belongs to S1 and AB belongs to S2, it implies AB belongs to S1 intersection S2. So therefore, again by previous property, previous theorem, A minus B belongs to S1 and AB belongs to S1, it implies S1 and S2 is a, so which implies S1 intersection S2 is a subring by previous theorem, is a subring. Okay, very simple theorems are there.